So transportation engineering consists of the entire network of moving material or humans from point A to point B. And that includes highways and railways, airports, and we have to consider a whole variety of factors: the terrain, the distance, the capacity that's necessary, etc. And so in our section, we are considering our focus on highway capacity. How many cars are going to pass a particular point over a given period of time? How many people can we deliver? How many cars can we deliver from point A to point B? So we want to study some of those concepts. So there are three primary variables that we need to make sure that we identify for ourselves. First is capacity, and that's going to be measured in cars per hour. And so that's the number of cars that can pass a certain point over the course of 1 hour. Then we have the speed of the car, so that's going to be the velocity in miles per hour. And then, of course, we also have to consider the density. So that's going to be the number of cars per mile of a stretch of roadway at any given instant. And so these three variables tie in together in the equation that we see here. So the capacity in cars per hour is equal to the velocity, the speed at which the cars are traveling, times the density of the cars, number of cars per mile. We can see that the units work out just fine. We get the miles canceling each other out here, and we get the same units on the right as we have on the left, cars per hour. So our first example ties those three variables together. So we have a survey team that's monitoring traffic on a one-lane section of highway. And from the helicopter we observed that we've got 160 cars in a 1 mile section, and the speed of the cars is a very slow 2.5 miles per hour. So we want to know how many cars are going to pass by a given point in 1 hour. So we're just solving for the capacity. So how many cars can be delivered past a certain point under these conditions. So we've got our capacity, which again is cars per hour. And so that's equal to just the velocity. So we've got our 2.5 miles per hour times the density, which in this case is that 160 cars per mile. And so it's just a straight multiplication question. So under these conditions, we can only deliver a pretty small number of 400 cars per mile. So over time, the guidance as to how close you should follow another car on the roadway has evolved. And so the original rule was the follow rule, followed by the 2-second rule, which is what I learned when I was learning how to drive, and now I think it's the 3-second rule, which is totally ridiculous and impractical. But the follow rule stated that there should be 1 car length between vehicles for every 10 miles per hour of speed. So we can see this here. The number of car lengths between cars is going to be equal to the velocity, so the speed at which the cars are traveling in miles per hour, divided by 10, and the units there are miles per hour per car length. And so we can see that that would work out if we divided those. Miles per hour will cancel each other out, and so then we've got car lengths in the bottom of the bottom, so those will move up to the top. So ultimately we'll end up with those units. So each car effectively under these circumstances occupies its own footprint. So if we have our car here, thank you very much for your compliments on my artistry, but we have the footprint of the car plus whatever space there is in front of the next car. So this is the footprint that a car occupies. So that footprint, the amount of space that it takes, we'll call that L road. So the length of road that it occupies. So that's going to be the length of the car times 1 plus whatever the velocity is divided by 10. So the 1 accounting for the length of the car, and then the V over 10 accounting for the space that we should leave based on the speed. And so again, those units will end up in miles per car. So that's the footprint for each car. And so with units of length, we've got L road is going to, units of length per car, L road is the reciprocal of density. If you'll recall, density is cars per mile, so cars over distance. This is distance over cars. So if we take the reciprocal, that's going to give us the density. So density is equal to the reciprocal of this L road. And so if we estimate that a car is about 0.0025 miles, which is about 13-ish feet, not an unreasonable estimate, makes for a pretty nice convenient number to use in our calculation here. So we've got this reciprocal of L road, so that's going to be the length of the car, that's our L car there, the 0.0025, times the 1 plus V over 10, and again the units of that are going to be the reciprocal of what we saw up here. Instead of miles per car, it's going to be cars per mile. And so then, if we multiply density times velocity times the speed, we're going to get the capacity. So what we're arriving at here is an equation that connects the capacity that the number of cars that we can deliver to a particular, past a particular point per hour is going to be based off of the velocity of the cars, and we've got this estimate of the car length. So now we can calculate the capacity based on the speed of traffic as it's moving down the road. So let's see how increasing the speed at which the cars are traveling following this follow rule affects the density and ultimately the capacity, our ability to deliver cars per hour. So if you'll recall that density is the reciprocal of that L road length that a car occupies. And so the formula we had for that was 1 over 0.0025 miles times 1 plus V over 10. So I just want to have that in front of us here. And then to get the capacity, we're just going to take the velocity and then multiply it by this expression right here. So if we plug in a speed of 0, so again, we're plugging that speed in here in place of the velocity. So basically, we just have the reciprocal of 0.0025. And so if we plug that in on our calculator, we're going to find that our density is going to be 400 cars, but we're not going to have any capacity because when I multiply that by a velocity of 0, I'm going to get no cars moving. So hopefully that makes sense. Now if we plug in 10, so if I go 10 in place of V here, I end up with 10 divided by 10 is 1, plus 1 is 2. So basically my density is going to be half as much, but my capacity now, at least I'm going to get some cars through. So 10 times 200, I'm going to get 2,000 cars per hour passing through. And so if we continue, we can keep on plugging in ever increasing speeds. We can use Excel with some formulas to kind of help ourselves out. But we end up with, sorry, this should be 133, 100, 80, 66.7, 57.1, stray mark there, my apologies. We get 50, 44.4, 40, 36.4. So these are just all the densities that are generated by plugging these speeds in for V into our density equation here. And for our capacity, it's certainly going to increase, but as we're going to see here, we're not increasing to infinity. As we look at these values, when we multiply these densities by these speeds, so we're at 3340, we keep on going, we get to about 3640 here. Now obviously we're traveling at 100 miles per hour, so without some sort of like automated technology we're going to struggle there, but if we had the automated technology we'd have a lot more density possible. But you can see that our rate of increase of capacity is slowing down even though we're increasing our speeds. And so ultimately what this leads to, if we were to extend this even farther, increase the speeds, we don't blow up to infinity, but instead we top out at 4,000 cars per hour. So this is the theoretical maximum that we could deliver under this follow rule, leaving this amount of space, following that rule for the amount of space between cars.